Welcome back. Hope you are well. Now, usually U substitution is something that is introduced before the fundamental theorem of calculus in our usual treatment of Calculus 1, but that is mostly because we want to give students a little bit more understanding about what the integral can actually do before we end up going and saying, okay, here is this pinnacle of education when we get to this point. So pedagogically, because we're not giving a rigorous treatment of the the integration by substitution comes later. Now, because we have the fundamental theorem calculus under our belt and a more rigorous standpoint at this time, we can actually go through and show that integration by substitution is good. And while we're doing that, we'll go ahead and throw in integration by parts as well. These are two huge applications because they greatly broaden the number of integrals that we can go through and integrate at this point. Before, we would have to go through and do a lot of guess and check to see if the derivative of a function indeed gives you whatever the integrand is going to be. If you ever could, then that's how you could do this. But there's actually a procedural way to figure out how to find this indefinite integral by using some of these techniques like integration by parts and substitution. So we'll go through and show why these techniques work like this here. And I'll also see at this point that integration takes a little bit more finesse, I should say, to work through, because derivatives you can kind of follow through a certain number set of rules. Integration, on the other hand, requires a little bit more creativity. We'll show in some places how these methods work and some places in which these methods don't work, even though you're trying to use the principles that we are laying out here. Now, first is integration by parts. So let's start by remembering what integration by parts does. The way that I'd like to try and explain integration by parts is that it is this taking the fundamental theorem of calculus together with the product rule and combining these together. We know that the product rule states that if you take the derivative of two functions, multiply together, fg, then what you get is f prime g plus fg prime. Now, there's a little bit of kind of what's going on right there in this as well, because what would happen if I were to add over this term in the theorem statement, the integral of from a to b of f times g prime plus f prime times g. That's exactly the integral of this part of this statement right here. And you can notice that what happens when I integrate that is what I get is f times g prime. Indeed, when I integrate something that is the derivative, then by the fundamental theorem of calculus, I'm just plugging in final minus initial, plugging in the final limit, the minus plugging in the initial limit. So there's a little bit of vestiges here of what the product rule is doing. But let's go ahead and walk through this again, this time with a little bit more care to each step. So what we do first in order to show integration by parts, which is this thing that says if I want to integrate from a to b of f times g prime dx, then the thing that I can do is I could just plug in final minus initial into the function fg. Sometimes this is written in this way. Minus, we can then subtract the integral from a to b of f prime times g dx. So the way that we do this proof is we first notice the product rule, and we're going to use the fact that integral works as an antiderivative for good classes of functions. Here we have that f and g are differentiable on the integral from a to b. That was something that we saw, I believe, in the second part of the fundamental theorem of calculus, if I remember correctly. Might have been the first. It's one of those two. Well, the functions f, g, f prime, and g prime are all going to be integrable by our conditions. Here, f prime and g prime must also be integrable as one of our conditions. So the products f prime g and f g prime also are going to be integrable. So this is something that I can take, and I can use this integral if I need to. Now, f g prime is also integrable on a to b. And why is this? Because this is just the sum of these two functions right here. So the fundamental theorem of calculus allows us to, this is the second part here, to write that this is the integral from a to b of f g prime of x dx. And using the fundamental theorem of calculus part 2, that's in this part, then we can say that that's final minus initial of the actual function f times g. Then we just go through and say, okay, well, what's another way to write fg prime? And that's using the product rule down here in this expression. And that's exactly what we need to get this statement of this theorem. A corollary of this is this. If I want to now, instead of trying to find definite integrals, I can now want to find indefinite integrals, then I don't have to worry about that final minus initial business. Instead, I know that the derivative of fg prime is fg prime plus f prime g, thanks to our previous theorem. And so because of this, we can just write this little slightly simpler formula here for finding indefinite integrals. Now, one way that we can simplify this even further is to use what is known as the Leibniz differential of a function, which is defined to be df, for a function f. That function is going to be defined to be f prime of x dx. This should look a little bit, by the way, kind of like u substitution, although we are going to go through and actually talk about u substitution in its own part here. We're just going to use this as a notation saver. So this is going to be the derivative of f with respect to x times dx whenever I write df. So there's another notation of it given here. Now, the formula of integration by parts can be written as in terms of definite integrals like this. We can write this as the integral from a to b of f dg. Notice that we're replacing g prime of x dx with this Leibniz differential. Can be equal to f times g going from a to b minus the integral from a to b of g df. Simplifying that down for indefinite integrals, we get something like this. Just the integral of f dg equals fg minus the integral of g df. This is exactly what happens when we do this oftentimes in an introduction to calculus course. Usually instead of f and g, you are seeing u and v, right? You might recall the integral of u dv equals uv minus the integral of v du. This is exactly the Leibniz differential that we're choosing to use here. Now, some examples of this. For example, one popular integral to kind of give and stump students when they're just starting to learn integration by parts is the integral of log of x dx, because they say, John, where can you use integration by parts here? There's only one function being multiplied. So what am I going to set to be my u or my dv in this case? Well, we're writing it, but it's going to be my f. What's going to be my dg? The neat little trick is that one gets to be a function as well. I could set, for example, f to be log of x, and I could say that dg is just going to be 1 dx, so that this is the integral f dg. When I go through and apply this formula to this, then this is what I end up getting. I get x log of x, that is the multiplication of f times g, and then I'm going to have just the integral of x times 1 over x in the integral to be subtracted. That's the minus the integral of 1, which gives me x plus c. So that's exactly what this formula is here. Now, one thing to do and make sure that we're kind of careful with whenever we apply integration by parts, it comes up with the second integral here, going from 0 to pi over 2 of x times sine of x dx. And the question is what am I going to do with this integral? What am I going to choose as my f? What am I going to choose as my dg? And you can see here that even though one seems to be prominent over the other, it's not necessarily true that in this case f is equal to x and that dg is equal to sine of x dx, because I have other choices. I could have said f equals sine of x and dg equals x dx. The question is, which one gets me to a simpler integral to solve on the right-hand side of that integration by parts formula? Whenever I try and figure that out, that's what I should be aiming toward when utilizing this formula. So what I do is I say, okay, well, maybe I get started in one direction or the other and see if it ends up getting me anywhere. If it doesn't get me anywhere, maybe I'll try to use the other direction. And of course, how can I forget? There's always the option of just plugging in 1 for one of your functions, right? And that might be something that's useful here. Or in fact, that dg is just 1 dx, for example. Well, for this one, it turns out that this is the option that works out a little bit nicely. And a little bit of the intuitive reason as to why is that we recall that the function that we're going to be writing this as is going to be fg minus the integral of g df. So whatever f is going to become df over on the right-hand side. The derivative of x is just 1, and that's pretty nice and easy to solve. Whereas turning dg into g, right, is what function g, when I take its derivative, gives me sine of x, I only get negative cosine. And so what I have over here is negative cosine of x times 1 dx. So putting all of that stuff together, I have that this is going to be equal to x times negative cosine of x plus the integral of cosine of x dx. Of course, we are evaluating this going from 0 to pi over 2. So if I want to convert this into definite integrals, then I could just evaluate like this. When I put all of that together, that should give me the answer that I'm looking for. It should give me the answer of 1, because this is actually going to zero out. The rest of it is going to be the integral from 0 to pi over 2 of cosine of x. That is equal to sine of x evaluated from 0 to pi over 2, and that should give me 1. All right, so this gets us a little bit more of intuition as to where the integration by parts formula comes from. Another good example is whenever you need to integrate by parts several times. Sometimes these things have to chain together, like in the example of the integral of log cubed of x. So that's what we're going to do. We're going to string this together in a particular way. Remember that with the log of x example, we said let's let our dg equal 1 dx. And that's exactly what we're going to do here. Here, f is log cubed of x. Now, when I go through and write out what this integral is, I don't actually get something that's simpler. I get something that's like this. But I do see that at least one thing has changed. Although I've gained a constant of 3 down here, I've also reduced the power of log cubed by 1. I have x logs cubed of x that I could just keep on the outside here, therefore, and then just continue to try the same sort of integration by parts in this second integral. Indeed, for this one, I'm going to choose that f is log squared of x, and that dg is 1 dx. And if I go through and do this again, I'm going to get an even simpler integral. In fact, now this time I have 6 times the integral of log of x, and I have that formula. Putting everything together there gets us our formula for this. So sometimes integrating by parts several times is necessary to get a good answer here. Now let's talk about a change of variable in an integral. Here is our theorem for this. And we'll see where the kind of change of variable comes in as we move on. Let's take phi to be some sort of continuously differentiable function. And let's have it be on a closed, when we say non-degenerate, we just mean not a point interval going from A to B. And f is being continuous on the range of phi inside of this interval from A to B. Then if I want to rewrite the function f, then I certainly can. I can rewrite the function f with respect to a particular other function written here inside. And this expression right here should look a little familiar. Remember that we said the integration by parts was combining the fundamental theorem of calculus with the product rule. What rule is probably being used if I see something like this in the integrand? That's right, we should be seeing the chain rule being used here. This is going to be combining the fundamental theorem of calculus with the chain rule for this formula. Here you can see this is f of phi of x times phi prime of x for a particular function. This is dx, and so all of these bounds are given in terms of x. However, you can see over here on the left-hand side, we have that our bounds of our integral have changed. Our bottom integral became phi of a. Our top integral limit became phi of b. That's because whenever we change everything to be in terms of our new variable, which is going to be determined by what phi is as a function, we get to change everything to be in terms of that new variable, including our limits. And we'll see that here through a few examples after we've gone through this proof. Now, some remarks before we get there, though, is that one of the things that oftentimes is used in graduate level mathematics is that we ask for this particular function to be strictly monotone. That's going to be the second bullet point down here. And that's because that's going to give us a more accurate description of what's going on with our function. At least less information is lost than if you are, say, plugging in something that is constant on a particular point. It's easier for us to say, work with the function a little bit nicer that way. That way, we can also plug in whatever kind of numbers that we would like, especially if this function is bijective. Or rather, that it's easier for me to know exactly what these numbers are going to be. I'm not just coming right back down toward it. But the theorem is going to hold even without this assumption. We prefer phi to be strictly monotone, but we're going to see some examples of where maybe when we make phi something that's not bijective, this ends up not working. That's in particular, that's going to be something that works not in our favor there. In particular, when it is not going to be surjective, that's when we'll see kind of a little bit of an example of when this type of principle does not work very well for us. Another thing that can happen is that when you plug things in to get your new limits for your integral, it might very well be possible that here you had a was less than b, but phi of a has no need to be less than phi of b. Even in the case of it being strictly monotone, this could be a decreasing function. In that case, we are just going to say that the integral going from c to d, if I ever need to flip those limits, I can do that as long as I put a minus sign in front of that. This works very well with our principle that the integral from c to d of f dx is plus the integral of d to c of f dx should indeed be equal to the integral from c to c of f dx, thanks to one of our theorems from before. And we know that this integral should be 0. So let's go through this proof real quick. First thing first, we're going to go through and define a few functions. We can recognize this big F as fulfilling the same role as big F did in our proof of the fundamental theorem of calculus. Here, we're going to start from some phi of a, this kind of beginning point for our interval, and then we're going to let our variable determine the top limit of this integral. So this is very much that antiderivative type function for definite integrals that we were given for the fundamental theorem of calculus. Then let's also define g of x to be a similar type of integral, this time using the base of a and going up and letting our variable be the top limit here for this integral, this being the second integral given in our formula for the change of variables. Now the fundamental theorem of calculus gets to apply. Because we have these being in the same form as those from the fundamental theorem of calculus, we know the derivatives of each of these functions is just the function that you see inside of the integrand. Here for capital F, the derivative of that is little f, and the derivative of capital G is going to be f of phi of x times phi prime of x. Now, let's go through and check out how this chain rule works. What happens if I take f and I try and compose phi in the middle here? So let's take a look at what happens when I look at phi of phi f of phi prime of x. That's a tongue twister. The reason that we're doing this is that we have a lot of information about f, and we can tie in phi here. If we do that, then we should find that we are getting something very close to what we're looking at down here. Maybe there's a way to connect these two functions. Let's see what we end up getting. Well, we have f of phi prime of x. That's going to give us f prime of phi of x. We know exactly what that is, thanks to what we stated before. That's little f of phi of x times phi prime of x. Well, that's exactly g prime of x. That means that these two things are both are the same antiderivative of a specific function. That means that the derivative of their difference is going to give us 0. Hence, the difference between them is a constant. Well, we need to figure out what that constant is if we're going to be able to move forward. So let's see if we can figure that out. Well, maybe I could go through and try and just plug in a point. If I do, I can plug in the point, maybe, for example, of b in for each of these. Then that's going to give me f of phi of b minus g of b. Well, that's going to be equal to, when I go through and figure out what this is, give me a second here. Here we go. Notice that if we had plugged in for u, we had plugged in phi of a, and had done the same thing, plugged in a here for x, then we would notice that immediately these two integrals are 0 because their bottom and top limits are both the same. So subtracting these two things together, it turns out that that constant of difference is going to be 0. So that's true regardless of where you are in the entire function, including at b, at the very end point. Hence, the difference between these two must be the same constant. It must be equal to 0. But that's exactly, if I plug in b for each of these x values inside of this formula, then I get exactly this equation. So this is the way of going through and proving that change of variables works. Now, how does this go through and apply? One of those things that we see it in a lot of is that, well, we could use this for indefinite integrals, like right here. The integral of f phi of x times phi prime of x dx. Normally, we would, in an introductory calculus course, refer to this as a du. Then this would be equal to capital F of phi of x plus c. This being the capital F that we saw in the theorem statement. So for example, we might go through and say, okay, let's take a look at sine squared of 2x. And for utilizing this, we are going to go ahead and keep with the notation of a variable u for these things. Now, integrating this, I first want to try and say, okay, what happens if I make u equal to 2x? In that case, the function du is going to be 2 times dx. If I were to just write this in terms of a phi of x formula, then this would be phi of x equals 2x. And then phi prime of x dx would be equal to 2 dx. And that helps us tie in here to the formula that we were given in our theorem statement. But even getting to that point, I don't really have much to go off of, so I have to use a trigonometric formula. The trigonometric formula I use is this double angle formula for cosine, rewritten slightly. Once we do this, we can rewrite sine squared of 2x equals to 1 minus cosine 4x over 2. And at this point, we can attempt a u substitution, this time making u equal to 4x. And you can see how that's written here. Here, this is our du from before. In this case, it's just d of 4x, written in terms of the Leibniz differential here, 4x being our function that we're working with. So this is 1 minus cosine of 4x over 8 d 4x. That's exactly what we are making our u over here. And now we can go through and integrate. Notice that something else changes as we go over here and change things in terms of u. This is exactly where we are using that change of variables formula. Notice that the limits change. The limits change. The bottom limit stays the same. It goes from 0 to 0, but the top limit goes from pi to 4 pi. What we are doing is we are plugging in the x values, 0 and pi, in for this substituting in function, u equals 4x. So that's just going to become 4 times pi right here. Sometimes I noticed that when I went through and looked at introductory calculus textbooks, sometimes they will just leave this limit right there and say, I'm going to go through and plug that in later on. But there can arise some issues from that, and we'll see that in a future example. Let's take a look at this one here. Let's take a look at examples of the integral going from 0 to 1/2 of x over the square root of 1 minus x squared dx. To integrate this function, we got to find a u to go in, and the u that we choose is this one down here, because this is, without choosing some sort of u substitution here, this integral seems a little tricky to take. What are the actual ways for me to kind of navigate through this function? But if I say, okay, I'm going to try and think of this as perhaps something that looks something like 1 over the square root of u, then I have something that is easier to work with. Right now, that's not what this is. It's actually x over the square root of u. But the question is, how can I get rid of that x? Well, the x is going to get absorbed here in determining what my du is going to be. So you can see here, first things first, I go through and write what my u is in terms of everything given here. I'm going to go ahead and replace out dx with d of 1 minus x squared, knowing that that differential is going to be minus 2x dx. But when I do that, I'm dividing out that minus 2 in order to, I can bring that outside the integral. But I'm also dividing by x. I'm also dividing by x, and that's going to leave me just a 1 in the numerator rather than the x from before. Substituting in my u and changing my limits here, I notice that my limits end up going to be decreasing from bottom to top now. And again, that's okay. We can always switch that to become going from bottom to top instead if we just make our outside positive rather than negative. Notice now we've also brought in the 2 into the integral, because that gives us a very nice definite integral, square root of u. Going through and plugging in what those limits are, I get something going from 3/4 to 1. So plugging in everything there gives us our answer. Here's another one. This is the integral from 0 to 1 of 1 over 4 minus x squared dx. Now, you may remember this one from a while back. It kind of depends on where we kind of are. But there are some interesting substitutions that we can do with trigonometric functions whenever we see integrals like this. In particular, I might notice that if this had been 1 minus x squared, then I could have plugged in x equals sine of t. If I had done that, well, dx would have been cosine of t. I'll get to that in a little bit. But the reason that we might choose this is that when I plug in that x is sine of t here, I have the square root of 1 minus sine squared of t. Well, this is, using the fact that sine squared plus cosine squared equals 1, this just gives us cosine squared of t on the inside of this integral. So this is cosine of t here. Now, if I'm multiplying that, if I'm taking the fact that dx is cosine of t dt, well, in order for me to get this to be in terms of dt, I must divide by that cosine of t. So that's one thing that ends up being useful here. In this case, we have something slightly different. We have 4 minus x squared, but if we make the substitute x equals 2 sine of t here, then we're actually okay. You can see here what happens in this denominator. You get the square root of 4 minus 2 sine of t quantity squared. That's going to give you the square root of 4 minus 4 sine squared of t. You basically can factor out of 4. Now you have 4 times 1 minus sine squared of t, just like we had before. That's 4 times cosine of t, and then indeed, just like that, everything else gets to cancel out nicely. But you notice that we did have to change our limits in order to make that substitution. So we get the integral to be just pi over 6. Now, this is a very neat trigonometric substitution rule. Unfortunately, it is not something that works in every single instance. Let's say, for example, we had something like this. Let's say we're taking the integral from 0 to 3 of x times the cube root of 1 minus x squared dx. And let's say that we try to use that here, because again, I'm noticing that I have a 1 minus x squared that I can work with here. So here we have x equals the sine of t. All right, and we could go through and find out what dx is going to be, cosine of t dt, past that point. But the issue is going to be what? Has anybody spotted it yet? It's going to be in trying to figure out what these limits become. The limits going from 0 to 3. These are limits in terms of x. So the question is, what's going to happen here if I try and figure out t values that work well for this? Well, if x is equal to 0, then I automatically know that t is going to be equal to 0. I can just say sine of t is 0, so I can just be working in that rotation. But if x is equal to 3, then I'm asking for a value of t such that 3 is equal to sine of t. Well, that's not going to happen. So this substitution does not work. This is the counterexample that I was mentioning before of when changes of variables can actually be a little bit tricky. Sometimes there's an issue with them, the function that you're using, the phi that you choose here, to not be surjective, so that you cannot actually find limits for this with respect to that substitution. Now, this one you may have already noticed has another substitution. You can just say u equals 1 minus x squared and be able to go on your merry way. But this is not something that is always the case. And so something we have to be picky of is knowing when we are making good substitutions and when maybe the substitutions maybe need to take a little bit more effort. So instead, let's go through and try and do another example here. And let's make that integral the following. Let's take a look at the integral from 0 to 1 of the square root of 1 minus x squared dx. Now, this one, we can ask the question. We have something that has the square root of 1 minus x squared in it. So we can ask, is it okay for us to use x equals sine of t? Well, if we take a look at our bounds here, it seems like we're going from 0 to 1 in terms of x, and both of those have values of t that satisfy those. So yes, we really should be fine there. So we're going to go ahead and continue with this. In this case, dx is equal to cosine of t, dt. And then this is going to be the integral from what? It's going to be from 0, because that is when x is 0. We can know that sine of 0 is equal to 0. That's plugging that in right here. And then it's going to go up the way to pi over 2. And that's because when we plug in sine of pi over 2, we're going to get that this is equal to 1. So we're plugging in those particular values there. Of what? Well, we've already shown that this is going to be the cosine of t. Maybe better to say this is the absolute value of cosine of t, something that I left off in my previous part, because remember, we're taking the square root of 1 minus x squared thing. And technically, what you get is the square root of cosine squared of t. So what that ends up being is the absolute value of cosine of t, my mistake from before. Now, dx is cosine of t dt, so I'm just going to multiply that out here on the side. Finally, I'm going to take a look here and notice that the absolute values are a little bit extraneous, because if I take a look at what my range is, I'm going from 0 to pi over 2. In all of those places, cosine is non-negative, so we are okay and good to go. Now, you might have said, John, there's more particular bounds that I could have chosen. Why didn't I choose 0 and 5 pi over 2, or 0 and negative 3 pi over 2? The idea is that we are traveling going from 0 to 1. Let me check something real quick. Thanks for letting me pause there. I was about to say something wrong. So we can notice that we're taking the path going from 0 to 1, but there could be potentially multiple different angles that give us these values of 0 and 1. The reason is due to kind of this notion of monotone that we were talking about before. Briefly, in order for me not to get into any of those sorts of details, it's okay if we stick to the values that are given to us by the inverse functions of sine given here. So for example, I can know what value I need to plug in here because this is the value given to me by sine inverse of 1. And this is the value given to me by sine inverse of 0. So if I'm trying to kind of stay out of the woods of that, then this is what I end up getting. But this is the issue with making a substitution for something that is not monotone as a function, is that it can be a little bit tricky to know what exact things I need to be plugging in there. This is a problem of our function not being injective, right? So strictly monotone is something that's very neat and can kind of help us get away from something like this. But we always know that we're in the clear if we're working with sine inverse of 1, sine inverse of 0 in these sorts of instances. And indeed, in this case, it does matter because when I integrate cosine squared, which is what this ends up being, what I'm going to get is something like this, right? It's going to be, I'm going to have to use a formula for what cosine squared of t is equal to. And I'm going to use a double angle formula to help me out with that. If I go through and do that, then I think I'm going to get cosine of 2t plus 1 over 2. So if I go through and integrate this function, in particular, I have a 1/2 that I'm trying to integrate. So I'm going to have t over 2 in that solution. That matters then what these bounds are going to be. It won't matter for the cosine part. You can go through and determine that yourself, but it will matter for the 1/2 part. It's just something to kind of keep in mind and be careful of whenever we make these sorts of substitutions. Let's do one more example to show the versatility here of the U substitution way. So let's take the indefinite integral here of this function. This is the square root of 1 plus the fourth root of x in the numerator of the function, divided by 2 square root of x, all dx. To find this integral, we're going to change the variable 2 times. We're going to choose 1 first. That allows us to think about getting the denominator out of the way. Well, there's a couple of choices that we have here. It turns out that a neat one to be thinking of here is looking at this being u equal to the square root of x. The reason that we might want to make u equal to square root of x here is that I notice that this here in the denominator is the derivative of u of square root of x, which is 1 over 2 square root of x. So indeed, when I go through and write this out, the denominator is gone. Now notice that the square root of 1 plus the fourth root of x becomes what? The square root of 1 plus the square root of u. And that's because that's the relationship between this and the square root of x, is that we are just taking the square root of the square root of x to get the fourth root of x. Now, this is something that we still cannot integrate, but we can try and be a little bit more creative now about how we want to do this. Now, if I give this to somebody just starting out in calculus, I think that there's still a little bit of confusion as to what do I actually make equal to, my variable equal to. But now that we've seen and cataloged that little log of x example from the integration by parts, there is a solution that's available to us. What if we made the entire thing our variable? What if we said let w equal the square root of 1 plus the square root of u? Well, let's see what happens. Remember that in this point, we're going to have to change out, if this is our variable, du as well. So let's go through and calculate what du is going to be. In order to do that, let's start by solving for u. U is equal to the quantity w squared minus 1 quantity squared. So that du is equal to the derivative of that, which ends up being 4w cubed minus 4w dw. Now, why is that useful? Well, if I'm integrating w du, then I can replace that with dw by just multiplying by 4w cubed minus 4w. And what I see here is something that is something possible for me to integrate. Going through and substituting in what I get after all of that and making sure it all is in terms of x, since I'm doing an indefinite integral here, I get this value for this integral. And that's going to do it for us today. These are 2 very important applications here of the integral, and are going to be pivotal for us moving forward. We're going to essentially want to really be able to use these in things that are coming up for us in the future. But thank you so much. Have a wonderful day.